Good morning, dear student. In today's lecture, we discuss the experiment number second from your practical course CHG 290 section second. That is to determine the equivalent conductivity at infinite dilution and the dissociation constant of acetic acid by conductometry. So we know that according to Arrhenius theory, strong electrolyte. So in conductometry, we know that this acetic acid is a weak electrolyte. So according to the RNS theory, strong electrolyte such as sodium chloride, HCl, and sodium acetate, sodium acetate, it is completely dissociate. So they dissociate completely dissociate completely at all concentration at all concentration dissociate at all concentration, and there is a linear increase in the equivalent conductivity. The second important point is that we know that the strong electrolytes such as NaCl, HCl, sodium acetate dissociate completely at all concentration, and the linear increase in the equivalent conductivity. So equivalent conductivity, it is directly proportional. Equivalent conductivity is directly proportional with dilution. With dilution, that is equivalent conductance of this strong electrolyte, it is increases with dilution. With increases with dilution, the increase in the equivalent conductivity, it the decrease in the sorry the increase in the equivalent conductivity with dilution is attributed with the decrease in interionic interaction. So the equivalent conductivity, it is increases. The equivalent conductivity, it is increases with dilution, and the increase in the equivalent conductivity with dilution is attributed with decrease a decrease of interionic interaction. Interionic interaction. Interionic interaction. This results into increase in migration of a speed of the ion with dilution, and hence the equivalent conductivity is also increases. So the 2 point is very important, that is for the strong electrolytes are completely dissociate and the equivalent conductivity is directly proportional to the dilution. That is with increasing dilution the equivalent conductivity is increases, and the variation of this equivalent conductivity with concentration for strong electrolyte, the variation of this equivalent conductivity with concentration for strong electrolyte in dilute solution was expressed by the following Debye-Huckel-Onsager equation. So this is your very well famous, very famous equation, that is Debye-Huckel-Onsager equation, that is the equivalent conductivity, which is equal to the equivalent conductivity at infinite dilution minus in bracket A plus B lambda infinity into under root of concentration. So this is the equation, that is Debye-Huckel-Onsager equation for the equivalent conductivity with concentration for strong electrolyte with dilution. So what it indicates? The equivalent conductivity is directly proportional to the square root of concentration. So where C is your concentration, C is your concentration of electrolyte, C is your concentration of electrolyte, and A and B are the constant for the medium. So A and B are the constant for the medium, constant for the medium. The equation, this equation satisfy the equation of straight line, that is y which is equal to mx plus c, where c is your intercept, m is your slope. x is your concentration and y is your response. And if you plot the graph of this equivalent conductivity lambda v versus under root of concentration, then we get a straight line graph. Then we get a straight line graph. Then we get a straight line graph. And the equivalent conductivity at zero concentration or the equivalent conductivity at infinite dilution can be obtained by the extrapolating the graph to zero concentration. So when you plot the graph of this equivalent conductivity versus under root of c, then this is a straight line graph, and we can easily find out the value, that is the equivalent conductivity at infinite dilution, by extrapolating the graph to zero concentration. The equivalent conductivity at zero concentration, the equivalent conductivity at zero concentration, that is at infinite dilution, means the equivalent conductivity at infinite dilution can be easily calculated by extrapolating the graph to zero concentration. So with the help of this equation we can easily find out the equivalent conductivity at infinite dilution. This is all about for the strong electrolyte. But in this practical, we determine the dissociation constant of acetic acid, and we know that acetic acid is weak electrolyte. So whenever we dissolve this acetic acid in water, it dissociates partly. The dissociation of the molecule of weak electrolyte increases with dilution. Okay, so this acetic acid, when it is dissolved in water, it will dissociate to give CH3CO minus ion plus H plus ion. We know that the Ostwald employed the law of mass action to the partly dissociated and undissociated electrolyte at constant temperature, which is expressed as, so we know that, that is Ostwald gives the equation, that is law of mass action to the partly dissociate, which is not completely dissociated at constant temperature. So the dissociation constant according to this Ostwald law, it is given as Ka, which is equal to, for this acetic acid, that is concentration of the product, that is negatively charged ion into concentration of cation, concentration of anion into concentration of cation divided by the concentration of the reactant, that is concentration of acetic acid. In general, if you consider in general, we can write uh, Ha for weak acid. So Ha for weak acid, and the dissociation constant is written, that is for Ka, that is Ka for this Ha, because Ha, it is denoted for, it is a symbol for weak acid. So Ka, which is equal to the concentration of H plus ions into concentration of A minus ion upon concentration of Ha, and this is known as Ostwald dilution law. So let us consider alpha is the degree of dissociation at given concentration. So alpha is the degree of dissociation, alpha is the degree of dissociation at given concentration, and 1 gram equivalent, alpha is the degree of dissociation at given concentration, and 1 gram equivalent of acid is dissolved in v liters of water, then v liters of water, then the equilibrium in the above, then in the above equilibrium, that is, so let us discuss, this is for the dissociation constant for weak acid. Weak acid is denoted by Ha, so it is given as concentration of H plus into concentration of A minus ion upon concentration of H. So let us consider the condition, that is alpha is the degree of dissociation at given concentration, and 1 gram equivalent of acid is dissolved in v liters of water. And then let us discuss for this acetic acid, that is dissociation, CH3COOH, it gives CH3COO minus plus H plus, and we know that the alpha is your degree of dissociation Alpha is the degree of dissociation at given concentration, and 1 gram equivalent of acid is dissolved. So the concentration of this acetic acid which is remain, it is given as 1 minus alpha. So alpha is your dissociate degree of dissociation. So after dissociation we get this ions. So alpha is your degree of dissociation, and 1 gram equivalent of acid is dissolved in v liters of water, and therefore the concentration of this acetic acid is nothing but your 1 minus alpha. So the alpha upon v, that is degree of dissociation divided by volume in liters of water, is equal to the concentration of CH3COO minus, which is equal to the concentration of H plus ions. So alpha upon V, that is degree of dissociation upon volume in liters of water, is given, which is equal to the concentration of acetate ion, or which is equal to concentration of H plus ions. And if you consider 1 minus alpha upon V, 1 minus alpha upon V is the concentration of undissociated acetic acid, undissociated acetic acid. So alpha upon V is the concentration of the particles, that is positively and negatively charged particle, and 1 minus alpha upon V is the concentration of undissociated acetic acid. So substituting this value into Ostwald dilution law, that is Ka, which is equal to, so what you get here, we get this, that is Ka, which is equal to what is the value, if you consider the value of this CH3CO minus is alpha upon V. So we know that this K is given as CH3COO minus into H plus upon concentration of acetic acid. So we can substitute the values, that is CH3CO minus is alpha upon V into alpha upon V divided by what is the value of this as concentration of acetic acid, it is 1 minus alpha upon V. And if we solve this, so what we get here, we get this, that is alpha square upon V 1 minus alpha. So this is your Ka, that is dissociation constant, which is equal to alpha square upon V 1 minus alpha, or we can write Ka, which is equal to C into alpha square, C into alpha square 1 minus alpha, C into alpha square 1 minus alpha, where 1 upon V is nothing but your concentration, that is C. So this equation, that is K, which is equal to alpha square upon V in bracket 1 minus alpha. So we can write dissociation constant, which is equal to C into alpha square 1 minus alpha, C into alpha square upon 1 minus alpha, because 1 upon V is nothing but your concentration. And with the help of this equation we can easily find out if you find out the degree of dissociation after the conductivity measurement, and if you know the value of degree of dissociation and the concentration is given, and we can easily find out the dissociation constant for this acetic acid. So let's discuss the practical procedure for this determination. So first we required, so what is the material we required for this experiment? We required the instrument, that is the conductometer. We required instrument, that is conductometer, and then we required thermostat, conductometer, conductivity cell is there. Then we required water. We required a different concentration of 0.01 normal KCl, then 0.05 normal CH3COO sodium acetate, 0.05 normal NaCl, and 0.05 normal hydrochloric acid, and 0.1 normal acetic acid. So the procedure is slightly different from your practical book, because I'm using the old book for this experiment. In this case, uh, what is the use of this solution, that is sodium acetate is NaCl and HCl, because they are strong electrolyte, and we can easily find out the equivalent conductivity for the strong electrolyte at infinite dilution. And we know that the equivalent conductivity is an additive property. So if we know the equivalent conductivity of this sodium acetate, NaCl and HCl, we can easily find out the equivalent conductivity of acetic acid at infinite dilution. And therefore in all process, they have used different concentration, that is 0.05 normal sodium acetate, 0.05 normal NaCl, and 0.05 normal HCl. Then you have to prepare different concentration from this stock solution, that is 0.05 normal, and find out the equivalent conductivity uh, at given dilution, and plot the graph and easily find out the equivalent conductivity at infinite dilution. And with the help of this, we can easily find out the equivalent conductivity for this acetic acid, because the equivalent conductivity is an additive property. Equivalent conductivity is an additive property, and therefore in material we require this. In the new book it is not given. So by using graph we can easily find out the equivalent conductivity for acetic acid. So in old book this procedure is given. So you must understand how one can easily find out the equivalent conductivity at infinite dilution. So we require this, and we require zero point 0.1 normal acetic acid solution. We have to prepare different concentration, measure the conductance, find out specific conductance, equivalent conductance, and then degree of dissociation and dissociation constant for this acetic acid solution. So let us discuss the procedure. That is first, that is the part first is your determination of cell constant. Determination of cell constant. Determination of cell constant. So it is very simple. So you have to just prepare 0.01 normal KCl solution and find out the cell constant. That is cell constant, which is equal to the specific conductivity of 0.01 normal KCl at 25 or at 30 degrees Celsius divided by the conductivity, that is observed conductivity. So whatever the solution which is you prepare, the observed conductivity of 0.01 normal KCl. So observed conductivity of 0.01 normal KCl solution. So with the help of this formula, we can easily find out the cell constant. So before determining the cell constant, you must calibrate the instrument, that is conductometer, and we are very much familiar from TYBSC. So how to calibrate this conductometer? So first find out the cell constant. After that, the determination, that is determination of equivalent conductivity. Part second is determination of equivalent conductivity. Equivalent conductivity of acetic acid at infinite dilution. So with the help of this strong electrolyte, one can easily find out the equivalent conductivity at infinite dilution for the weak electrolyte. So you just prepare different concentration from this 0.05 normal sodium acetate, NaCl, and hydrochloric acid, and measure the conductivity of this solution. And then you have to plot the graph, that is you have to find out the specific conductance by using the formula cell constant into observed conductance, equivalent conductance, and then you have to find out the equivalent conductivity, that is specific conductance into volume equivalent. And then you have to plot the graph. Then you have to plot the graph of the equivalent conductivity versus the square root of concentration, and we get a straight line graph. So we get a straight line graph, and if you plot this graph to this line, we get here the lambda infinity value. So if you plot a graph of equivalent conductivity versus under root of concentration, and if you plot this graph to this y-axis, extrapolate this graph on y-axis, we can easily find out lambda infinity for the strong electrolyte. And we know that the lambda, that is the equivalent conductivity, is your additive property. So the equivalent conductivity at infinite dilution for acetic acid, we can easily find out if the equivalent conductivity of strong electrolyte is known. That is, we can write lambda infinity for sodium acetate plus lambda infinity of hydrochloric acid minus the lambda infinity of HCl. So with the help of this, so by measuring the conductance of different concentration of this sodium acetate, HCl and NaCl, it is not HCl, it is NaCl. You have to find out, you have to plot the graph of equivalent conductivity versus under root of concentration, and then you have to find out the lambda infinity value for this strong electrolyte, and with the help of this equation we can easily find out lambda infinity for acetic acid. This is the old book, therefore we use this procedure. So let us discuss about the third part, that is determination of dissociation constant of acetic acid. So the third part is what? You have to find out the dissociation constant for acetic acid. So you have to prepare different concentration. You have to prepare different concentration from stock solution of zero point 0.1 normal, zero point 0.1 normal acetic acid. So you have to prepare different concentration. That is, you have to prepare 0.1. So you have to measure the conductance of this 0.1 normal solution. Then you have to prepare 0.05 normal. Then you have to prepare 0.025 normal. Then you have to prepare 0.0125 normal. So the preparation from the stock solution is very simple. You have to use this formula, that is N1 V1, which is equal to N2 V2. So N1 is your known concentration. So V1, which is how to find out, N2 how to prepare 0.05, and how much you prepare, that is V2. So with the help of this formula, you have to prepare this different concentration and measure the conductance of this solution. So if you consider uh, the observation table, that is we required concentration, that is zero point 0.1 normal, then 0.05, then 0.025, and then 0.0125. Then in the second, you have to measure the conductance. So for every solution you have to find out the conductance, that is observed conductance. Okay, having a unit of mho, mho. So you have to find out the conductance for this solution. After that, you have to find out the specific conductance. Specific conductance. So how one can find out the specific conductance for this solution? Specific conductance is very simple. So you just multiply the observed conductance into cell constant. So just multiply observed conductance into cell constant, so we get specific conductance. So it is very simple. So first you have to measure the conductance by conductometry, then find out specific conductance, that is observed conductance into cell constant, and then the third one, that is you have to find out the equivalent conductance. The third important uh, part of this observation table is equivalent conductance, and the equivalent one conductance we can easily find out with this formula, that is specific conductance into 1000 divided by concentration. So with the help of this formula we can easily find out the equivalent conductance. Then you have to find out the degree of dissociation, that is alpha. So first you have to find out the conductance, then you have to find out the specific conductance, then you have to find out equivalent conductance, and after that you have to find out the degree of dissociation, that is alpha. Degree of dissociation, that is your alpha, and the alpha is given by the formula, that is the equivalent conductivity at given dilution divided by the equivalent conductivity at infinite dilution. So we can easily this value is known, that is your equivalent conductance for different concentration, and this value is obtained from the strong electrolyte, that is lambda infinity. So you have to find out the degree of dissociation, and finally you have to find out the K for a different concentration, and if K is you, what is our formula? C into alpha square 1 minus alpha. So with the help of this equation we can easily find out the dissociation constant for a weak acetic acid. So this is very simple practical. So you just understand the conductivity, conductometer, the different terms involved in conductivity, that is specific conductance, equivalent conductance, what is conductance, what is resistance, okay, specific conductance, equivalent conductance, degree of dissociation, and dissociation cost. So this is all about the determination of, that is determination of equivalent conductivity at infinite dilution and the dissociation constant of acetic acid. In the next lecture we discuss the remaining practical. Thank you.